So my name is Juliet, and I'm happy to meet you all. And I'm interested in my field area for my master's program. I studied data science, but for my bachelor's, I studied applied mathematics. And moving forward, I've, I've developed a special lab for quantum machine learning through the guidance of Prof. June Zwan. Yes. So that is how my quantum machine journey has actually begun. So today I'm going to speak on robust data encodings for quantum classifiers. So the first thing I'd like us to know is that this field of quantum computing is quite new. There are lots of research ongoing, so it's at its foundation. Okay, so I'm moving on. So for today, this is the outline we have, what you are going to be looking at. You're going to be looking at quantum machine learning. I'll briefly speak about it since Prof. June touched on it in the previous presentation. I'll also speak on quantum classifiers. I also have a look at robust data encodings. We'll look at what is data encoding. We'll look at the classification of robust data points for a single qubit classifier. And we'll look at some future works that we can also have in our research works. Okay, so in this slide, we can see a picture. So this picture, it shouldn't confuse you. It's just trying to let us see how things are done within quantum machine learning. So over here, you can see the initial qubit state. So just like you do in machine learning, where you have your data set, where you split your data set into the training data and your test data. So over here, we have our input data here. And if you look at this critically, you can see that this looks almost like a deep learning neural network, like a convolutional neural network. So over here, you have some layers here. And these layers, this is where your data is being transformed for you to have your prediction or your output data. So you would look up here, you see something, I've written here qubits. So in quantum machine learning, one of the most popular words you hear is qubits. Qubits is just a representation of data that's your quantum model work with. So if you are using any quantum model, you can't have your data, unlike the classical machine learning, where the data is represented in bits. With the quantum machine learning, your data is being transformed into qubits. So qubits is speaking in a more simple terms, it's just your transformation of data. So everything you see here in these stages is just a representation of these qubits. So we'll get to understand as we move on. So my question is, where are we and what lies in the future for quantum computing? So apparently we are actually in the era of noisy intermediate scale quantum, which equates to quantum devices that don't have many useful qubits and possess high error rates. Current quantum processors in libraries in laboratories or in the cloud contain fewer than 100 qubits with short lifetimes. So what this is trying to say is that currently we are in the noisy intermediate scale quantum. That means that in this quantum computing era we are in, there is still some noise in the models we use. Noise meaning that, when you are working with a model, you want to achieve accurate predictions. But because of the state of the quantum computing we have, there is still some errors inside somewhere. So research work is being done in this area to minimize these errors, or better still, achieve 100% accuracy. So in about 10 years, we are looking at correcting these quantum errors. That's why we have this quantum error correction. Able to construct very large quantum computers without noise, so that researchers should use this quantum error correction with about we have about 50 to 100 qubits available with the quantum computing, yes. So we don't have much qubits, and these qubits too are very achieving high accuracy. Okay, so I move on, please. So now we heard of quantum classifiers, but it's not anything strange. So when we consider binary quantum classifiers, you can just simply call them quantum classifier. So in this case, in my case, we focus on the a binary classification like a yes meet framework for quantum machine learning. Please, should I continue? Okay.
Yeah, please.
Okay, sure.
Signal come back.
Oh, okay, sure.
Yeah, please go ahead.
Things we need to consider. So you will need a quantum neural network. You also need some parameters, because in building your model, you will include some parameters, and then you also need to process your data. I wouldn't talk much because I'll talk about it in the next few slides. Then over here, you see a quantum classifier is essentially the same as a classical one, because the key difference between the model is the answers of the classifier. So when we talk about answers, we are just talking about a measurement, some assumptions we make with our models. So with the normal classical machine learning models, you have the only difference models and the quantum machine learning models is just the parameters that we use. So meaning that you can have similar models, but the changes in parameters is what makes the difference. So unlike classical methods, quantum classifiers require pre-processing to encode classical data into quantum data, quantum neural network. So if we compare, so looking at the classical methods and then the quantum machine learning methods, one difference, or as compared to the classical methods, you can do a few corrections in your data set, and then you fit it into your model. But with the quantum machine learning models, you have to transform your data set. You cannot use the data in its raw form. You have to transform it, which I'll talk about more in the slides. Okay. So up here, you can see variational algorithms. So I'll also speak about it in the next slides. So we need to know some examples of some quantum machine learning classifiers that we have available now. So some people have done research around this and then tested these models or classifiers. So we have the support vector classification with quantum kernel. We have the quantum support vector classifier. We have the variational quantum classifier. We have the circuit quantum neural network classifier. So for this work, we had a look at the variational quantum classifier. The reason being that it's really, so far, is the best model that works well with binary classification. Because in this work, we looked at a binary classification problem. Okay, so now we've heard of data encoding, but let us know what is data encoding. It's nothing strange. So data encoding, so I read, for nearly all quantum machine learning problems, a person challenge is inputting arbitrary data into the model such that the quantum neural network can process it. This input process is known as data encoding. So data encoding is simply the transformations that we make to the data set before we can use it in the quantum models. So now the encoding can be thought of as loading a data point X belonging to a bigger domain X from memory into a quantum state so that it can be processed by a quantum neural network. The loading is accomplished by encoding from the set X to n qubit quantum state. So as I mentioned before, and I'll mention more in the next slides, the encoding is just simply your data in its raw state being transformed into the quantum state before it can be processed by your quantum neural networks. Meaning that these quantum neural networks cannot work with just any data at all. You need to transform your data. Okay, so now we mentioned robust data encodings. So a picture up here, you see something like a globe, and then over here you see something like a plotted graph. So this is a simple depiction of how this whole this whole transformation happens. So we see that in the when transforming your data set into the quantum state, normally you see it in the form of an orbit where you have your data points. The reason being that quantum computing, there are some parameters or there are some things that hold it, called the superposition and then the entanglement. So with that, it's trying to tell us that when you have your data set, normally a data can exist as bits, zeros and ones. But in this case, we are trying to say that a data can exist or it can be in the form of a spin, such that you cannot just predict the state of a data at once. We are trying to say that, if you have a coin and then you spin the coin, a coin normally has a head and tail. But when the coin is in a spinning mode, you cannot really tell whether you land a head or a tail. We have both outcomes coming out as possible outcomes. So in that same way, we look at a data in a quantum state, it's seen in this kind of a format. So let me read what is down here. We said that let E be a quantum channel and consider a binary quantum classifier with decision rule, Y cap. We say that the state, row X belonging to the domain, encoding the data point X belonging to X robust point of the quantum classifier, if and only if your predicted Y with the E into brackets or row X is the same as. So what this is just trying to say is that when you have your data in the raw state, and then it's being transformed into the quantum state, as you see in the orbit, it should be the same. There shouldn't be any change, because when you are encoding data, we have different types of encoding data. So with the one that I know, which is the basis encoding of data, with that one, if your data, let's say you have a data X, and the representation of that data in bits is maybe 1011. When it is being transformed into a quantum state, it should still maintain those properties. It shouldn't change. You should still see it as 101, but just that this time around, it's in the quantum format. Okay, so I move on. So as I just mentioned, you don't use just any encoding for any data type. Depending on the kind of data you are using, it will sort of require you to use either of these encoding types. Well, over here, I just tried to explain what everything meant here. So the points with the green outlines are correctly classified. Then the points with the red outlines are misclassified. And then the black dotted lines represent if you see very well, yes, you will see that there are some misclassified data points. But if you look on the B, you realize that the misclassified data points have reduced. And then you see that your decision boundary too has changed. We need to make sure that when you have these data points where you have these ones, we normally want them to be well separated. Okay, so depending on the parameters that you put in place, that is what affects you making a very good or drawing a very good decision boundary. So in plays a very important role in when building these models. Because if you see for the first one, it's quite okay. And then the second one is sort of the best, the picture in blue. We had a very good decision boundary line. So it means that creating parameters in a quantum model is very, very important. The parameters that you put in place it plays very key role in achieving good results. So with the paper I used, okay, they tried when they tested, they tried different data encodings. So they looked at the dense angle, they look at the wave function, they look at the super dense that they didn't do it themselves, and another group of researchers worked on that. But for this paper I read, they worked on these three, and then they got very good accuracy results. But for the super dense angle, there was a problem because you can see the accuracy is very low. So is present is still there's still more work that has to be done in terms of the parameters that are being put in place and how the model is even being structured, and even the type of data encoding. As I mentioned before, to achieve a better, you need to put in the best parameters. Okay. So over here, I was just trying to speak about the outcomes, what everything represented here. So we are looking at transducing quantum data to quantum memory for learning with exponentially less data. And then we know that working with the data, having less data is one of the major challenges with classical computing, especially, or classical machine learning. You need a very large data set to be able to train a good model. But we are looking for a better way of achieving good models, but with less data. So generation of more quantum data, exactly. That's also another challenge because with quantum computing, you definitely need to transform the data, except for if you are using a quantum computer. But if you are using a classical computer, you need to transform these data. And also we need to have a look at other quantum classifiers. We need to test more quantum models on the NISQ computer. We also need to practice with more data sets and try different encodings on these different data sets to see how best they work with these different data sets. So I would like to acknowledge these researchers. So Ryan LaRose and Brian Coyle, I got the paper from them. And then Nana Liu and Akin Tiku, these people were acknowledged by Ryan LaRose. And then Ju Zhuang, my supervisor, I'd like to acknowledge you. And then Institute for Quantum Computing, Beidou Incorporation. So all these people, I got information from them while preparing these slides. Thank you very much.
Thank you. Thank you for your presentation.
Thank you as well.
Thank you.
It's very, very good. Oh, any questions?
I guess.
I
Or
got
you
a
go
question.
first.
So, what would it take to put this data into quantum memory? Do you know? It's okay if you don't.
Please, can you come again?
I was saying, how could you encode this classical data into quantum memory?
Yeah, so
If you
okay,
have
so
an
with the
idea of
data
how to do that.
Okay, so please, I read about it. I haven't
Oh,
tried it myself. I only read about it and saw.
No.
Hello, Julia. I think we lost you. Julia, I stay here.
maybe.
Transformation.
Hello, Juliet. The signal is cut off. Do you mind if you explain this again?
Oh, there she goes. Oh wait.
Sorry, I think it was my network.
Oh, the signal is
Sorry,
cut.
I didn't realize. Yeah, I didn't realize when the network here. Okay, so please, I was saying that I would like to repeat myself. So
Okay.
I was saying that yes, personally, I've not tried the data encoding myself. I only read about it. So with what I saw, I see a lot of mathematics behind this.
Uh-oh. She paused again. Your connection dropped out. You could turn off your video. That would help with bandwidth.
Say I read about it, but I'm not.
Yeah,
Yes,
yeah,
please. I don't know if
it, I agree with Adam. Maybe turn off your video would be
I should
helpful.
turn off my video.
Yeah, that may be helpful. Yes.
Okay, sure. I have now. Yeah, is it better now?
Yeah, it's better.
Yeah, that should
Okay,
reduce your lag.
okay. Yeah. So please, is it okay now?
Yes,
Mhm.
Yep.
yes.
Okay, sure. Adam, I don't know if I answered you well enough because I have very little information with the data encoding because I've not had a hands-on with it. I only read about it.
Yeah, that's okay. I wasn't expecting you to have known to do it. Your experiment was mainly with testing if you could get binary quantum classifiers to be accurate with different
Yes,
data encodings.
yes.
I don't even know how you build a quantum memory. The idea of a quantum CPU is new to me.
Yeah, even me.
I don't know how you
Because
build a quantum RAM system.
it's
I had a
really
sorry, I just had a quick question about, I guess, like the noise that is coming in.
yeah.
So when you are training this data or trying to classify this data, when you are trying to encode it, are you saying that once you do the encoding, that encoding is already wrong because of that noise? Or is it you do the encoding and then when you try and do these classifications, the state becomes corrupted or whatever and is noisy?
Oh, okay. Okay, so with the issue about the noise in the data, so far the algorithms that are being tested that works well is a variational algorithms, variational quantum algorithms. Yes, they work best with
Mhm.
data now. They are much resistant to the noise in your data set.
Mhm.
As in when it's being encoded, they are much those algorithms are the best assistants now. Yes.
Right. Okay. So you're saying that like I guess some encoding algorithm is really noisy, but they're trying other things to other
Yes, yes,
algorithms to okay,
yes,
gotcha.
yes.
And then I guess also too, like when you then classify that encoded data, does that become noisy as well after that classification, or are you able to get
Okay, so yeah, so
reliable results?
another thing I forgot to mention is with the data sets to, we need like they are also trying to look for some specific data sets that work best for these models. Because I think if they
Mhm.
had the right fit data sets, these models would have been working much better. But right now we are trying to use
Mhm.
the classical data, transforming it into the quantum state before we try to fit them into these models. Yes. So the issue has to do with these data sets that we have exactly. It should have been in the best state, like we should have had them in the quantum state originally rather than
Mhm.
because in the quest of transforming, that is when I think all these noise come up. So right now
Right.
they are looking for ways, yes.
Huh.
Yeah.
Interesting. Thank you.
Oh, you're most welcome. Thank you too.
Thank you. Oh, I have another two questions. The first
English.
the first question is in your presentation you mentioned three types of encoding methods. So I'm wondering in what scenario you will prefer to choose one rather than the other one. For example, some angle encoding or amplitude encoding. So I would like to
Okay.
yeah for the scenario.
Oh, okay. So with the encoding, I think with the choice of, I think as it stands now, with the papers I had a look at, I think right now they can't really specify that. Maybe let's say if you're doing image classification, they can't really specify if maybe this encoding, maybe the basis encoding will work best for image classification, or maybe the angle will work best for image classification. As it stands now, they want you to try all the different encoding types for, even let's say we are looking at the iris data set, we would like to try all the different encoding types. Then from there, we can say that, okay, this type of encoding works best with this iris data set. So for my work, they looked at the iris data set, and then they saw that the super dense didn't work best. The accuracy was that low, but it worked for the basis encoding, and there's another one, the angle, that one worked best with the iris data set. So for a future work, we have to now look at different data sets like the MNIST data set and other kind of data set, audio and all, and then see for ourselves which encoding types will work best. Yes, please, I don't know if I've answered you to your, yeah. Is it okay?
Okay, yeah.
Is it okay?
Yeah, okay, thank you. Actually, you partially answered my second question. My second question is what's the advantage or disadvantage for these encoding methods?
In types. Okay. The advantage and disadvantage. I think maybe with the qubits that maybe are being used, because in the research work, I think the more the qubits, the higher the errors, but the less the qubits, the higher the accuracy, it looks like. So if you have an encoding type that uses more.
No.
Hello, Julia. We cannot hear you.
Yeah, we lost your connection again.
Yeah, hello.
Hello. Yeah, yes.
We can hear you
Yeah,
again.
sorry, my network here, the weather here. So I think, please, did you hear me?
Yes, I can hear you
Yeah, we
right.
hear you.
I don't know if I finished answering you, but the network just went off like that. But please, is it okay? Is it okay with the answer I gave?
Oh, I think we lost you in the second question.
Whilst
Half, maybe you the rest
come
half
again.
of the second questions.
Oh, okay. So should I come again? Should I
Okay.
come again?
Yeah.
Yeah.
Please explain the second question again. Thank you.
Okay, yes, please. Okay, sure. So your question,
Yes, my question.
my observation, right? Yeah, please can you ask again so that I
Yes, my second question is what's the advantage or disadvantage for this encoding method?
Oh, okay. Okay. So the first disadvantage I would like to speak about is the complexity of that encoding type. So among all the different encoding type, the basis encoding, I think, is the one that is easiest. It doesn't require much computation. So that one is much easier. So that's an advantage with that. It doesn't require a lot of maybe building any complex model or something of that sort. Yes. So that's it. Then another disadvantage with maybe the other encoding types could be the difficulty in making some computations, because for some of them you're dealing with some complex numbers and there's a whole lot of mathematics behind it, which is a bit complex. Yes. So that would be a disadvantage somehow, because you have to do all these calculations well enough to achieve accuracy. So and then another thing too is the data encoding, its capacity to
No.
that we are going to be please, is it okay? Is my network, can you still hear me?
Yes,
Yeah.
I can.
You can't
You're good
hear
now.
me. Okay, sure. Yeah, so data comes in different formats. So we when you are looking at text type of data, video type of data, picture, sound, so all these different type of data would require different manipulations on them and different memory capacity and different memory sizes. So with a disadvantage with some of them could be that maybe they may not have the capacity to contain all these different data types. That's another thing I would like to speak about. Yes. I didn't really I don't have much information to that, but they just a little knowledge I would like to speak on.
Oh, thank you for your answer.
So,
Yeah. By the way, in the email you said you have
I will correct.
want to share with us.
Yeah. Please come again.
In the email you said you have some experience want to share with us after the presentation.
Oh,
Anything
yes.
common?
Oh, okay. So I would it was quite a personal one to you, but I can say it here. I was just saying that I'm thankful to you for giving me this platform to present, because it has really brought a lot out in me, because I remember I told you that, oh, my interest area is in data science and all. I never thought of ever involving myself in quantum computing or quantum machine learning. But when I started reading, it was amazing. I was enjoying what I was seeing, and I'm very glad. So that's the experience I had. I saw that there's more I can learn, and I was just discovering a lot. Yes. So that's just the experience. It was a personal one I wanted to share with you. Yes, that I enjoyed what I did. Yes, please. So thank you so much.
Yeah, thank you. I appreciate your presentation efforts.
Yes, please.
Thank you for coming today also.
Yes, please. And thank you, Jack and Adam, for the questions. And thank you, June, for your
Yeah.
time. I'm happy to get to know you all.
You're welcome, Juliet.
Definitely.